Okay, welcome to another pre-lab video for the 1211 lab here at North Georgia. This week's experiment, we're going to be taking a look at solutions and precipitation reactions and really kind of focusing in on how do we actually make solutions. So getting kind of some familiarity like from a lab standpoint, like how do we go about making solutions typically, as well as then looking at a precipitation reaction and kind of some of the ways we write reactions for precipitation reactions, and also kind of using it as a way to review some stoichiometry that you guys have probably been going over in lecture. So as a starting point, I'm going to go over a little bit of just kind of really quick terminology. So when we talk about solutions, we're usually talking about some sort of what we call homogeneous mixture, which basically just means we have a nice even mix where all of our components are evenly distributed throughout the entire mixture itself. And if we take like one small part versus another small part, their compositions are exactly the same. And in these mixtures, we have multiple chemical species. Most of what we're going to be looking at really only has two chemical species, as far as kind of on the simplest side of things, that are not really reacting with one another. And so other terminologies that you'll typically hear for our solutions are that you'll hear things referred to as like a solute or a solvent, where the solute is typically the compound that you're dissolving usually in the solvent. And so a lot of the times, like for our lab this week, like the solutes are going to be like the ionic compounds that are dissolved in water, which is going to be our solvent. And more often than not for general chemistry, that's how most of our solutions will be. We'll probably have some sort of solid ionic compound dissolved in water typically that then we'll use to do our reactions. Now, last bit of terminology deals with concentration, like how do we express how much of something is dissolved in our solution? And so the most common way we express concentration is with units of what we call molarity, which is the moles of our solute in particular, divided by the total volume in liters for the whole solution that we're looking at. And that's by far the most common unit for concentration that we use, and really kind of the only main concentration we use throughout 1211. Now, making solutions. In terms of how we go about making solutions kind of in a lab setting, there's two main ways we're usually going to do this. The first and probably most common way is if you have a solid that you're basically a solid, in this case like an ionic compound, that you want to make a solution for, you can mass out how much of that solid you actually want to dissolve, measure the total volume at the end for your solution that you're making to be able to find concentration. Or for instance, if you know a specific concentration that you want and a specific volume, you can actually do kind of a quick calculation to figure out, well, how many moles of this compound would I need to have the correct concentration and molarity. And then if you know how many moles you need, you can convert that to a mass with molar mass. So there are some kind of unit conversions and kind of different dimensional analysis things that will show up a lot in these calculations for making solutions. But that's probably one of the most common ways to make them, because you can make solutions of a specific concentration this way by kind of doing the calculation in advance, knowing I need to dissolve this much in this, like this much of a compound mass-wise in this volume of a solution. Or, like I said, there's other ways you could do that too. If you just know the mass and the volume that you use, you can calculate what the concentration is if it's not important to have a certain concentration. The other way we often will make solutions is if we already have our solute dissolved in a solvent of some kind, is that we can change its concentration through what we call a dilution. Now, dilutions will only lower concentrations for things, but it's still really useful. Like if you have a really high concentration solution, like say like 1 or 2 molar solution, which is actually pretty concentrated, but we want a solution that's only like 0.15 molar. We can actually calculate then how much of our initial solution we would need to get to a specific concentration with a specific volume for like a final solution that we're interested in. That's one of the things you'll actually be doing in today's or in this week's lab is you're going to have a particular volume and a particular concentration you want for one of your chemical compounds in your reaction, and you're going to have an initial concentration of that compound in solution. So you have to figure out how much of that thing do I need to start with, and then add more solvent. You're always adding solvent to do a dilution, or in this case, water. How much more water do I have to add to my starting solution to get the correct final volume and concentration of things that I want? So those are kind of the two main ways to go about making solutions that you'll be getting some experience kind of doing both during this week's experiment. Now, for the reaction itself, talking about precipitation reactions, in terms of knowing like when is a reaction a precipitation reaction, kind of the easiest or generally, I think, kind of accepted definition is usually just you have two what we call soluble compounds, which are basically just things that dissolve normally in water, reacting to make one insoluble product, which is then something that really doesn't dissolve in water. It's going to be a solid at that point. And we refer to that solid product that you make in your reaction the precipitate. That's what we call it. So your precipitation reactions, you're always making a precipitate, some sort of insoluble solid compound, from two starting compounds that are soluble and are dissolved. So those two terms, like soluble versus insoluble, are really just all about whether that compound dissolves or not in water. And another note that I have here, I use this term dissociate here in the slide. Since most of what we're looking at for precipitation reactions are going to be ionic compounds. Ionic compounds, when you put them in water, if they dissolve because they actually dissociate or break apart into their individual ions. And so taking a look a little bit more at that, like the reactions and how we write reactions for precipitation reactions, at this point you're probably used to writing what's called molecular equations for reactions. Like anytime you've had to balance a chemical reaction or been looking at chemical reactions so far this semester in lecture, it's probably been a molecular equation, which is simply just going to give you like the actual full chemical formulas and the physical states of each of these for the full balanced reaction. Now, what happens though is if we look at all these different pieces, like their physical states tell us something, right? Aqueous phase here for our initial reactants. Any ionic compound that's aqueous phase in its molecular reaction or molecular equation basically means that compound is dissolving or it's soluble in water. And that also means that when you put it in water, it's breaking apart into its ions. And so our other ways of writing reactions are going to be looking at what happens when we break these things into their ions. Like what are the actual ions that are reacting and what ions are actually just kind of there but not necessarily doing anything. And so some other pieces of terminology here. If you have ionic compounds that are listed as aqueous, we will also refer to these as strong electrolytes. Anything that's a strong electrolyte is something that if you put it in water, it completely breaks apart into ions. So any aqueous phase ionic compound that we ever see written, we consider those to be strong electrolytes from a terminology standpoint. And that means that those aqueous ionic compounds, you're not going to find like this all still put together in water. It's going to be broken up into 2 potassium ions and a carbonate ion. Likewise, this one will have like a nickel and 2 chloride ions that it's going to break apart into. This, though, since it's a solid, this is not breaking apart. It's not dissolving in water, so it's that solid, that compound as a whole is still intact in water. Right, and so terminology-wise, again, since this is the solid being produced in this reaction from 2 things that were aqueous phase to start, like 2 aqueous things making a solid, this precipitation reaction, that solid then is our precipitate in this case. Now, other types of reactions or equations that we can write for precipitation reactions, we'll often write what's called a complete ionic equation. And this is basically just taking our reaction and everything that is going to dissociate into ions, we break them up into their individual ions. So from that previous slide, we had K2CO3, the potassium carbonate. Basically, all of our subscripts are going to become coefficients. So I back up for just 1 second. Like all of these subscripts are going to become coefficients unless the subscript is part of a polyatomic ion formula. So like the 3 for CO3 is going to stay a subscript in that complete ionic equation because this is really a polyatomic ion, and the polyatomics are not going to break apart. But really, if we have K2CO3, putting this in water, what we're actually going to make is 2 individual potassium ions and then 1 full carbonate ion. And so that's why those like subscripts are becoming coefficients, is those subscripts that describe like how many of that particular ion you have, it is breaking up into all the individual ions. And so when we look here, we see like for the potassium carbonate, we get 2K plus carbonate 2 minus. We're getting all the individual ions for those originally aqueous ionic compounds. We saw the same thing happening here for nickel chloride. We got the nickel 2 plus now, and then 2 Cl minus because we had 2 chlorines. It is the subscript that, again, is now the coefficient because it wasn't the polyatomic ion formula. Nickel carbonate stays the same, so it's just nickel 2 carbonate still here as a solid. And then we had 2 KCl at the end from the previous reaction the way it was written. And again, since KCl is aqueous phase, we break it into its ions. We're going to get 2 potassiums and 2 chlorides. And one of the most important things about writing these complete ionic equations, make sure you're listing the correct physical states for everything. All ions are always aqueous phase. Make sure you have the charges correct for everything, and make sure everything is balanced. Right? If we have 2 potassium ions on this side, there better be 2 potassiums over here somewhere on the right as well. And so everything needs to stay balanced throughout that whole process, which sounds pretty tedious, but is extremely important. You always want to make sure your reactions and your equations as you're writing them, that everything is balanced for those reactions as you do it. Now, one last bit of terminology here. If we're looking at this reaction, we actually notice that we have 2 potassium ions in the aqueous phase on the left, and then again 2 potassium ions in the aqueous phase on the right. And we see the same thing for the chloride ions. They're just the ions basically in the aqueous phase on both sides of the reaction. Any ions that are just their individual ions on both sides of the reaction, we call these spectator ions because they're not really doing anything in the reaction. They're in the solution from start to end, but they don't participate in any actual chemical reactions that are taking place. And that actually leads us to how we get what we call a net ionic reaction or equation for these precipitation reactions. And our net ionic equation is only going to show basically the ions that are reacting with each other. And so in this case, it's and typically for precipitation reactions, it's the ions making the precipitate itself. So here we have nickel 2 plus in the aqueous phase plus carbonate is going to make nickel carbonate as a solid. That would be our net ionic equation. We didn't show any potassium or chloride ions from the previous slide because all spectator ions, if they show up on both sides of the reaction, they kind of cancel out. And so they don't really participate in anything. And so it's just our ions really making the precipitate for these net ionic equations for all of our precipitation reactions. Now, in terms of kind of this last part here, how we know when we're going to get precipitates for putting different ion combinations together. This is where we're going to use something that, at least at the start here, is going to typically be given to you in class that we call solubility rules. Although your professors probably will make you learn a lot of these solubility rules for the lecture portion of the class. They might not give you these charts for exams, for instance. But using these solubility rules, you're typically going to see like here, there's a lot of trends. So like notice here, like this says soluble ionic compounds, and it has a list of ions. That basically means that all of these ions, whatever they're paired with, they're usually going to be soluble unless they're paired with one of these exceptions, right? So going kind of back to our previous one here, we actually had carbonate, which if we're looking at our chart is normally an insoluble ion. So carbonate's with the other insoluble ones. So carbonate is normally insoluble unless it gets paired with either ammonium or we call our alkali metal cations, where alkali metal cations are like group 1 metals like potassium or sodium or lithium. So if we kind of come back here, we notice, if we come back just a second, like if we were pairing carbonate with nickel, nickel is not one of those exceptions. So that means that nickel paired with carbonate should be insoluble because nickel wasn't one of the exceptions that would make it do something different. Whereas the original part of the reaction, the reactant side had potassium carbonate. Well, carbonate is normally insoluble, but potassium carbonate is soluble because potassium is one of these alkali metal cations that is the exception then for carbonate that will make it soluble instead of insoluble. And so that's kind of the general use of these solubility rules, is you're really just looking at, all right, what is the trend? And typically you're looking at the anions mostly, but I would often advise people, like if you see a group 1 metal, like group 1 metals are just always soluble. Like you see here, the exceptions for all these insoluble ones are always the alkali metals, your group 1 metals. So group 1 metal, it's going to be aqueous phase always for these different reaction equations that you're writing. But otherwise, you're typically looking at the anion and just seeing, all right, what's the normal anion trend? And is the cation an exception to make it do the opposite thing? And if the cation's not an exception, it does the normal trend, and now you know whether it's soluble or not. That's kind of the application of this, just sort of to show kind of one quick example and also look at how we predict products for these kind of reactions. Here we have strontium chloride plus lithium phosphate as our general reaction. How we go through and kind of exchange or figure out what our products are going to be is we're just doing an ion exchange, right? We have strontium, which is a cation. Lithium over here is a cation. So those two things, if they're both positively charged, can't really combine with each other. But what we can do is strontium can pair with the other anion, which will be phosphate, and lithium can pair with the other anion, which in this case would be chloride. And so writing a reaction, we can get strontium phosphate and lithium chloride. And notice as I write this reaction for the first time, I haven't balanced everything yet, but when you write your products, always write them so that the total charge of that compound is balanced, right? Phosphate here's a -3 ion, strontium here's a +2. So if I want a balanced ionic compound, I need SR3, I need 3 strontium ions to go with 2 phosphate so that this whole thing is neutral. And then I know this is actually going to be a solid based on those solubility rules, because if I look at, first off, strontium is not group 1, so I'm going to look for phosphate in that chart. And if I'm looking at this chart, here's phosphate. It's normally insoluble. The only things that are exceptions are ammonium and group 1 metals, those alkali metals. Well, strontium is a group 2, so it doesn't fit that. So strontium phosphate is going to be a solid. It's going to be insoluble like its normal trend for phosphate. And then my other product here is lithium chloride. Right? I have lithium pairing with chlorine instead. And again, write the formulas for these things based on charges. Lithium is +1, chlorine's -1, so it's a 1-to-1 ratio. We'll balance all of this in just a second with coefficients. So don't worry about the subscripts here too much when you first write your products. We'll get everything balanced kind of at the very end. For lithium chloride, we know this thing is going to be aqueous phase because lithium, being a group 1 metal, it's just always going to be aqueous phase no matter what. And so that right away pretty much tells us it should be aqueous. We could also look at chloride. Chloride is normally soluble, so it's normally going to be aqueous phase unless it's paired with, there's some heavy, if you go back and look, there's some pretty heavy elements that it can pair with, like silver, mercury, or lead that can make it insoluble or a solid. But that's not, lithium wasn't one of those, so it's just aqueous phase like normal. Now, for balancing on this, we do want to go through and balance things properly. So for instance here, if we have 3 strontiums on the right now I have none over here, that means I need a coefficient of a 3 over here, right? And that's going to give me 6 total chlorides, which means I'm going to have a 6 over here, and for me to have 6 lithiums, I'll need 2 of these lithium phosphates. And so you can kind of go through step by step, and we'll balance everything with coefficients. So write the products based on balancing charges for the individual compounds, find the phases from the solubility rules, and then balance everything at the very end with coefficients when you're writing these reactions. And that's usually the easiest way, I think, to go through a lot of these types of problems if you have to write products and balance these types of precipitation reactions. Now, I think that's plenty on the background here. So what I do want to spend some time on here kind of briefly before we wrap up is the experiment itself. The lab itself this week actually is relatively short, particularly if you are pretty comfortable making your solutions at the start. That's the part that really kind of probably takes the longest. The reaction itself happens very, very fast once you do it, and then it's just one filtration at the end and you're pretty much done. So for the experiment part here, you will be making solutions for both the sodium carbonate and the calcium chloride that you're going to be reacting. So the calcium chloride, you actually will see it in the bottle that it's in to kind of start with. It's calcium chloride dihydrate, and so you'll sometimes see its formula. You'll actually see the formula written this way. Hydrates, they'll have like this dot and some number of waters kind of with them. This is for those chemical compounds when they solidify, they actually trap water kind of in the solid in a proportional amount, like an actual kind of like whole like molar amount. And so for this compound, when you calculate the molar mass of this solid to figure out how to make the solution, do keep the waters as part of this thing's formula to find its molar mass. That is important, or else you will make a different concentration for your particular compound. So keep that in mind for your concentration. For the sodium carbonate, that one's going to be a solution already, and so you're really just going to be doing a dilution. So you're going to have an initial sodium carbonate concentration, and you're going to have to dilute it to get the correct amount with the correct concentration that you're going to use to do your reaction. Calcium carbonate is going to be a solid to start with. You're going to mass out the proper amount, make a solution out of it, and again, as you do that for the calculations, remember to count the water for your molar mass of the calcium chloride as you do that step. And then we're going to react these two things together to get a precipitate. I'll let you guys kind of go through and do kind of that, like I said, the ion exchange to write that reaction on your own. I think that's some of the pre-lab questions. We'll probably look at that as well as some of the post-lab. But what I want to hit on here is just kind of some general quick things in terms of like using a volumetric flask, which you'll be doing to make both of your solutions. So if you're using the volumetric to make a solution, kind of the best or most efficient way of usually doing it is you're going to add the appropriate amount of your solute, so whatever solid mass or like starting volume of your original solution that you're going to dilute, you're going to add that to the volumetric flask first, and then you're going to add water or whatever your solvent is. This week our solvent's just water. We're going to add water, and we'll typically use deionized water, particularly in this experiment, to fill up just below the little line that's going to be on the neck of your volumetric flask. And then you're going to mix that solution really thoroughly. We don't want to fill it all the way up to the line right away. We want to give everything a chance to mix really good, and so fill it up a little bit below the line, mix it up really good, and then once it's all mixed up good, then add that last little bit of water to get the right proper volume of everything. That way everything is nice and thoroughly mixed when you actually finished making your solution. So those are kind of the quick, just general steps. And again, your volumetric flasks, they basically look just kind of like a flask. It's got like a really kind of tall neck that's got a mark somewhere in the middle of it. And that mark is exactly the volume of that flask. So if you have like a 100 milliliter volumetric flask, if you fill it to that line on that neck, that's exactly 100 milliliters for the volume. And so these things are actually extremely accurate. And glass ones are extremely expensive, but that's why we actually are using the plastic ones for Gen Chem, is because we do know accidents happen, things get dropped. So just kind of a little bit of a safeguard, but these things are still very accurate in terms of the volumes that you're trying to measure with them. And so that's kind of the general procedure you'll be using for those volumetrics to actually make your solutions. Now, at the very end of the experiment, once you've made your solutions and you've mixed the two solutions basically together to make your precipitate, your solid precipitate at the end, which should be calcium carbonate, then you're going to do a quick what's called vacuum filtration to isolate your product. So a couple weeks ago for the separation lab, we did a gravity filtration where we had like our filter paper and a funnel, and we were kind of like waiting for things to drip through, where we were collecting our solid that wasn't dissolving and things on filter paper. This is kind of a similar idea. We're still going to be using filter paper, but we're going to have a slightly different shaped funnel, and we're going to use a vacuum to help make everything kind of go a little bit faster. And so for these the gravity filtration we did before, they're nice, but they can be a little bit slow. These vacuum filtrations, we're going to have something called a Buchner funnel that's basically already set up for you. All you're going to need is a piece of filter paper. It's going to be small and round that you can mass out ahead of time. And you're going to put that little filter paper on the Buchner funnel. It should fit really flush and nice. And then basically you should be able to turn on your vacuum. You'll hear kind of the hissing of air getting pulled through everything. And then you can go ahead and actually just do your filtration. It's fairly fast. The vacuum is actually going to help to pull your solution through the filter paper very quickly, and it will also help start to dry your remaining product, your solid product that should get stuck on the filter paper also pretty quickly. And that way, once all the solution is through and you've let it dry kind of on the vacuum filtration for like a minute or two, now you can go ahead and take your filter paper off, and you're going to dry that filter paper very briefly in the oven before you kind of mass your final product. And that will hopefully give yourself time for your filter paper to get dried out and get most of the water out of that. But that's kind of the last step of this week's reaction. So filtration, kind of already done it from one perspective, gravity filtration. Vacuum filtration, it's a little bit more convenient in terms of speed or how fast it can happen, but it's not always useful for depending on what kind of size of filter paper or what you're really trying to filter. There are some instances where vacuum filtration can be counterproductive because you might be pulling something through the filter paper just if the filter paper is not kind of fine enough to prevent solid from going through it. So if you have really solid, small kind of particulate parts or particles, those might actually get through the filter paper, get pulled through by the vacuum sometimes. So there are some times where vacuum filtration is not as good, which is why we do use both from time to time depending on the experiment. All right, I think that's pretty much everything I have for this week's lab. Like I said, the experiment should hopefully be relatively short, but there is quite a bit to do in terms of some of the calculations for figuring out how to make your solutions, as well as kind of some different reaction writing for precipitation reactions in general that you'll be doing for both the pre and the post-lab portions of this lab. And so if you do have questions on any of that, feel free to ask your professors. You can always email me back as well or talk to Dr. Meyer about it. I'd be happy to help anything that you guys have that you run into for this experiment. Hope everyone has a good week, and we'll see you next time.